Good evening, everyone. This is Astro 10, and I'm Celso Batalha. And let's see what's going on today. Um, in fact, this week we have a second midterm, and the midterm, as it happened, and the midterm number one is going to be on Thursday, October 27. So 1 week from now. So I will send reminder notes, but you should be able to not forget that. Now, because I'm a nice person, I have it's not a retake. The exam is not the same, but you have a second chance in case something goes wrong to access your exam again on Saturday. So that is the second attempt. And so you have access to one exam per day. So you cannot do two on Saturday, right? So you do one on Thursday, you do one on Saturday, which is a retake, and you pick the highest score of both. So try not to forget that. Make sure you give yourself some reasonable time to do your exam. Don't expect to do the last moment because sometimes problems arise, and you know all of that. So also this coming week um, we have extra credits, we have homeworks, and we are initiating a very important subject in this course, and perhaps is one or the second most important chapter in this course. I think I rank the first or the chapter that is most important, chapter number 4, the one that deals with light and the properties of light, and the chapter um, number 10, which is the one we initiate and we are going to be focusing this coming week, is perhaps the second most important. So why is that? So let's take a look at the PowerPoint and let me briefly go over it. So this chapter, it deals with measuring the stars. So I think somebody is coming up. I have two participants. Oh, Amanda. Hey, Amanda, how are you?
I'm okay.
So let me. Do you need to ask any question?
No.
No. Okay. All right. So I go on my monologue. Anytime you want to say something, just let me know. And I'm taping uh, this lecture. So, but this chapter. Oh, what am I doing with this? So this chapter is very important because it has to do with measuring the stars. When we think about science, we think about a method that allows us to ask questions on how the universe, how nature work. I mean, how everything that surrounds us work. That's what science does. I mean, science does not deal with absolute truth, trying to come up with truth about the universe. What we do is to come up with reasonable explanations on how nature works and to outline all the processes responsible for operating the changes that we observe every single moment of our lives. That's what science does. And science can be applied uh, to basically any data available. And um, and one of the outcomes of doing science is to create elaborate explanations as to how nature behaves the way it does. So if the explanation um, becomes robust and complex, we call that a theory. So we have a theory that explains how nature operates, like plate tectonic theory is a theory that explains how nature operates here on Earth in geologic scales and how mountains are formed, how volcanoes come to be what it is. So it's an entire theory. We um, went on 2 weeks ago. Now, one of the aspects of science or scientific enterprise is the ability of bringing to the laboratory objects we are studying. So we have a theory about how things behave, but the end of all our inquiry is data. Is what we can touch, feel, see, and manipulate and control. So ultimately, we bring things to the laboratory, and then we try to make sense of what we um, or of our explanations. So the question is, how can we do that with astronomy? Since objects that are targets of astronomical studies are so far away that we haven't visited them. So we haven't gone to even our closest star, which is the sun, we haven't gone there yet. We haven't, I mean, if we travel with the highest speed there is, which is the speed of light, it will take 4.3 years to arrive to the closest star system, that's Alpha Centauri. So let alone there is no technology available for that. So we can't do this kind of things. So we haven't visited quasars. We haven't pretty much visited the first ever formed galaxies in the universe, although we can see hints of them, but we haven't visited them yet. They are 10 billion light years away. We haven't gone there. So how can we talk about these things as if they were true objects, as if they really existed, if we haven't gone there yet? We haven't brought any of their materials to our laboratory and dissect them like we do in biology, like we do in physics, like we do with particles. We haven't done that yet. So the answer to this question is pretty much in this chapter, chapter number 10. So we know about stars because we, as it is said here, we understand the properties of lights and atoms. I mean, light is something, is a phenomena, is a, as we studied before in chapter 4, is a type of energy that interacts with matter, and matter made of protons, electrons, atoms. And when light interacts with atoms, it collects information about the environment where the atoms are located. So think about a star that is very far away. A star that is very far away, let's say 4 or 5 light years away, like Proxima Centauri. We haven't gone there, but light of these objects, of these stars, have been produced in an environment, in a gas, in an atmosphere that in which its properties like temperature, um, magnetism, uh, magnetic activity, chemical composition, all these features that are part of the atmosphere have been pressed in the light that left the star. So once we collect these lights with our telescopes, we can use the techniques you have been studying so far, photometry and spectroscopy, photometry is the technique that allows astronomers to measure the intensity of light that arrive to their telescopes on very specific colors, and also spectroscopy, which is the science that allows astronomers to take the light and open up in a rainbow and observe and analyze absorption and emission lines. And by doing so, they can pretty much tell a lot about the conditions of the atmosphere. So we don't need to go there. That's the main point. You don't go to the stars. We don't go to quasars. We don't go to Andromeda Galaxy, which is 3.5 million light years away. We don't go to these places, but light of all these different objects arrive at our telescopes and bring with it information about the places this light or those features of those lights were produced. And then astronomers, because they educate themselves, they go to graduate schools and they learn about these techniques, they can then use their skills to infer properties of all these objects. Any question, Amanda?
No.
Okay. So first one, how can we establish rulers to measure distance? How can we do that? So the first technique that is given in the book is called parallax. Let's see if I have here. Parallax is right there. So parallax is this. Let me see if I can go back here. So Earth, let's say today in this diagram, Earth is in a given position, right? Now 6 months later, Earth is going to be down here. And then in another 6 months, it's going to be up there. So Earth goes in a circular path around the sun. So imagine there is a star A that is closer to Earth or to the star system Earth-Sun than it is star B. So when Earth is on the top part of this curve and you look at star A, right there, so you see star A project as well as star B, you see both of them project in a given part of the sky. So here's given star A and star B, which is close to this star and this other star, but not so much of these other 4 stars. But then 6 months later, Earth goes and stays in the lower part. You look towards star A and star B, and you see them in a different position right here. So if you observe the sky with very meticulous care, and nowadays we can use photometry, we can take pictures of various small regions of the sky, patches of the sky. So if we do that and we find objects that move with respect to background stars, stars that are further out, we can, using a simple trigonometry, we can establish and determine what's called parallaxes. What that is? Well, if you look at this figure given, I don't know if you can see my hand tool. Let's see if I can get an annotator here. I don't think I can. So if you look at, no, it doesn't go. That's too bad. If you look at this, see this yellow mark? If you look at this angle is, apologize for that. This angle is given with simple geometry, is given by the ratio between the diameter of Earth orbit divided by the distance of that star to the sun itself. And we learned that in geometry, and the Greek knew about it, and they call those angles parallax. So if you can see the star A moving from this sky position to the sky position in 6 months, you know this angle in the sky is equivalent to half of this angle here, right? Or the equivalent to the diameter of Earth divided by the distance from Earth to the star. So parallax is a technique that allows astronomers to measure distance to nearby stars. So stars that are very far, parallax doesn't work, doesn't hold, but for nearby stars is a good one. So the greater the parallax, the closest the star is from us, and the smaller the parallax, the smaller the angle, it means the star is further out. So you get to a point that you cannot use parallax anymore to measure distance. So parallax is a technique that allows astronomers to measure distance to a nearby star just by observing them over a time period of 6 months. So nowadays, satellites are out there in space and they help us to measure with very good precision parallax to nearby stars. Now, there is another technique that is based on the fact that light falls with the square of the distance. It's called the inverse square law. Let me see if I have in here. The inverse square law, and I don't have that. The inverse square law is based on the fact if you are close to somebody speaking, you can hear well, but if that person goes further away, you can't hear that much, right? Because the sound diminishes with the distance. In fact, the intensity of the sound falls down with the square of the distance, not just with the distance, but with the square of the distance. For instance, you have somebody one meter from you. So then you have some sense of how high that sound is, or the sound the person is emitting is. And let's make an exercise and put that person not 1 meter away from you, but 3 meters away from you. The intensity of the sound will be lower, not by a factor of 3, but a factor of 3 squared, which is 9. So the sound is going to be 9 times dimmer than it is when the person was at 1 meter. So it falls with the square of the distance. This is a property of waves in general, and light behave that way. Now, why this inverse square law is so important for us? Well, because of the connection between brightness and luminosity. So what does this tell us? Something about distances. So look at this. What luminosity is? Luminosity of a star is the total amount of energy the star itself is sending out to the space in all directions. So that is the luminosity, is intrinsic to the star, is the energy itself the star produces. Think about energy as the ability to produce things, to do work, to generate work in the universe, heat and all of that. So luminosity is energy that comes out of the star. But this energy, since it spreads out in a volume, as this energy propagates, as this light propagates and moves away from the source of that light, its intensity falls. So that if you are close to the star, like we are close to the sun, we see the sun bright during daytime. But the sun is not the most luminous object in the sky. The sun is the brightest object in the sky because it's very close to us. Now, there are galaxies out there like Andromeda that harbor not just one star, but hundreds of billions of stars. Imagine the amount of energy of hundreds of billions of stars, some of them more energetic than the sun. So it's something fantastic, right? But if you look, I mean, we can't see Andromeda during daytime, first of all. And when you look in the direction of Andromeda at nighttime, we don't see it with a naked eye unless the sky is very, very dark. You are in a completely dark environment, like in Yosemite Park, and the moon is not in the sky, and so on and so on and so on. No one has a fire camp light up. And then you can look towards Andromeda, and then you might be able to see some patch, some ghostly illumination coming from there, right? Why is that? Why can't we see Andromeda that bright? Well, because Andromeda is not one astronomical unity away from us in distance. Andromeda is 3.5 billion, no, I'm sorry, 3.5 million light years away from us. 3.5 million light years away from us. So that light gets diluted when it moves and when it arrives towards us. So the amount of radiation, the amount of light we perceive as observers is called brightness. This term here, brightness, is the luminosity, which means the total energy, diluted by its distance squared. So when we receive them, it has been depleted because it has been expanded out and diluted. So when you go out and you look at the stars in the sky, you see them with different brightness. Why is that? Well, because some of them are bigger than others, but also because of distances. There is a factor distance that we cannot easily resolve, right? So how can we resolve this? With the inverse square law. If you happen to know how luminous an object is, like for instance, let's say we identify among the stars in the sky, we find some stars that are identical to our sun. So they are kind of a twin sisters of our sun. They are the same, right? They have the same spectral characteristics, they have the same coloration, they have the same everything. And then we say, okay, that star, for all that matters, is our sun. So if you find a sun that is at in a certain regions of the galaxy and you observe the sun, so and more than that, if you find how bright the sun is, how do we do that? Well, you got your telescope, you point to that hypothetical star, and then you collect the amount of radiation that star is sending, and we receive here. And by doing so, we apply the inverse square law. So the brightness we observe is equal to the luminosity we know the star produces divided by the square of its distance. There is a factor there of 4 pi, but don't worry about that. But you take the luminosity divided by the square of the distance, and you have the brightness, which means you have three quantities. So you have the brightness, basically. Brightness is equal to the luminosity divided by the square of the distance, which means you can determine the distance if you know the luminosity and brightness. Right? So that's the next way to get your distances. Now, chemical composition. How do we know about the chemical composition of stars? Well, we know because of spectroscopy. So atoms consist of protons, neutrons, and electrons. And protons and neutrons are found in the nucleus. In fact, the nucleus is a small, an atom itself, if you think about an atom, is something that is about 10 see if I can write. I don't think I can write. For some reason I can. Now I don't know what's going on here. I lost my PowerPoint. Oh, my PowerPoint has been. Look at this. Okay. So so let's see what it is. There you go. So an atom is an object that has a size, a diameter of 10 to minus 10 meters. And the nucleus is about 10,000 times smaller than that. So at 10 to minus 14 meters is just a small region of the entire atom, which is very small. So what we found by studying spectroscopy is that electrons, they cannot occupy any region they want around the nucleus. Like planets can be found at any given distance from the nucleus, and planets can, depending on the energetic of the star system, planets can be at any position. But when we go to the atomic environment, when we go to the very small part of the universe, to the atoms and protons and neutrons, we found that electrons cannot be at any place they want. In fact, electrons can only exist at very specific regions or distance from the nucleus, right? And which means when atoms receive energy, electrons are bound to go and jump in two energetic levels. When the energy is given to atoms, electrons move up to ulterior orbits or orbitals, and they stay there for a short time, and they go back to their original state or the state they were there previously. And when they do that, they release energy. So when you observe lights that comes from faraway objects, what we see is light is being depleted from the continuum of the star at very specific wavelengths, as we say, at very specific transitions. And then astronomers can use that information to figure out a chemical, not only chemical composition of stars, but also how hot they are, if they are moving towards us, the Doppler effect. So this week, the discussion we had this week was about Doppler effect. So Doppler effect is the one that is why Doppler effect exists. Well, when a source emits some sort of a radiation, if there is a relative velocity between the source and the observer, the frequency in which that radiation is produced is detected at a slightly different frequency. So if the source is moving towards us, there is a slightly increasing frequency. And if the source is moving away from us and that light is emitted, there is a slightly decreasing frequency or increasing wavelength. So that is the Doppler effect. And astronomers can use Doppler effect, which is pretty much based on these transition lines. So astronomers can use that to pin down the dynamics of a system, the orbital motion of stars around the center of mass, or how the universe is expanding, the dynamics of groups of galaxies, everything. So everything we want to infer as far as velocity and orbital motion is concerned, we can pretty much get that information using Doppler effect techniques. And that goes without saying chemical composition. So how do we know the chemical composition of stars? What is the percentage of calcium, magnesium, zinc, aluminum? We don't need to go to the star and collect a sample. We just observe the stellar atmosphere, and then we can make sense of the chemistry that goes in there. Here's an example of emission lines Um, and in the laboratory, we can measure these transitions at very specific wavelength and use those traces to identify elements in the laboratory. And then we go out and we observe stars and we identify the same elements in those stars, and then we can tell with certainty the stars have those particular elements. So, for instance, helium lines are always those. Neon lines are always those. Mercury are always those. Sodium has very specific transitions in a yellow band. That's why San Jose street light is like that. So here's an example of an spectra. And here's an example of that spectra as we detect it in the computer. So all these depletions we call absorption lines, you can see up here. See that? This absorption line corresponds to this line. This hydrogen line corresponds to this darkness. This line over here corresponds to that. So this is called a spectrum. So again, astronomers don't need to go to the stars to find out what they are made of or exactly find out what they are. So, and because the stars, they have spectral characteristics, some of these lines are stronger than others. Um, in the 20th century, it was developed what's called a spectral classification for stars. And the spectral classifications go O, B, A, F, G, K, M, which you can memorize. Although you're an online student, you might not need to memorize that much. But if you wanted, you could say, oh, be a fine girl, kiss me, or oh, be a fine guy, kiss me. That gives you the spectral classification of stars. And since technology improved so much since the 1900s, this spectral classification was improved further by adding numbers between those letters. Right. The star Sun is a G2 star. It's a star that happened to be in between the G and M, G and K type of star. So the G2 star is hotter than a G5 star, but it is cooler than a G0 star. So the numbers go from 0 to 9 in between those letters. And so temperature is also one obtained by either using spectroscopy. We do some modeling on what type of atmosphere is responsible for producing certain transitions, and but it can also be determined using photometry, the spread of colors in stars. So again, this chapter, Measuring Stars, it gives you tools and explains us how astronomers can grab information about stars, about galaxies, which is a collection of stars, without going there. I mean, we use light. We know how light behave in the laboratory. We see and we know how light interacts with matter, how transitions occur, and then we apply this knowledge to understand stars and quasars and galaxies. That's pretty much this chapter. Um, do you have any question, Amanda?
No.
No? Okay. For now, let me just stop